Hi, in this video we are discussing dimensionality reduction with kernel principal component analysis. In abbreviated form we call it as PCA. We shall be discussing this one with one sample Python code and with lots of explanation. Principal component analysis, that is PCA. It is a simple yet popular and useful linear transformation technique that is used in numerous applications such as the stock market predictions, the analysis of a gene and then expressing data and many more applications. And the main goal of PCA analysis is to identify the pattern in data, and PCA aims to detect the correlation between the variables. If a strong correlation between variable exists, the attempt to reduce the dimensionality only makes sense. We know that whenever we have a data set, the data set will have multiple input variables and say one output variable in case of supervised learning and no output variable in case of unsupervised learning. So now what will happen if we consider all the feature variables in our model design, in our model training, then there is a finite probability that the model may get overfitted. And we know that in some cases, if we have number of input variables or feature variables more than 4, so that can also make our model overfitted. So that's why we should eliminate those feature variables or input variables which are not decisive. So how to get this idea that which feature variables will be considering in the final model design and training and testing? So in that case we can go for this PCA, that is principal component analysis. So we'll be selecting those feature variables as a principal component which will be used in our training and testing purpose and model design purpose. So how to get this idea? In that case we know that whenever one variable is decisive for another variable's value, then we should expect a high correlation coefficient between them. We know that correlation means the respective relationship between two variables. One is the input variable, another one is the output variable. So now what will happen? We know that to measure the correlation, we are having the concept of correlation coefficient, which will vary from +1 to -1. +1 means strong correlation, where when one variable is increasing, the other dependent variable will be also increasing, and when it is decreasing, that one will be decreasing. In case of negative correlation, when one variable increases, the other variable decreases, and vice versa. So in this way we are supposed to find out those principal components, those principal attributes which will be decisive in the output decision. So as a result of that, my model's dimension will get reduced. As a result of that, the computational complexity will be reduced and my model will have a better prediction and forecasting. So in a nutshell, so that is what PCA is all about, is finding the directions of maximum variance in high dimensional data and project it onto a smaller dimensional subspace while retaining most of the information. So PCA using Python, here we are having the module SK, that is the scikit-learn, is a more common way of speeding up a machine learning algorithm is by using the principal component analysis, that is PCA. In our learning, the algorithm will be too slow because the input dimension will be too high. Then using this PCA to speed it up can be a reasonable choice. So for the better understanding, let us go for one sample coding. So here we have imported all the required modules which will be required in our coding. So here we are having the Irish dataset. Irish dataset you can easily download from the net. So I've kept this one in a certain folder. Also I can use the GitHub link or any online link to access this iris.csv. CSV means the comma separated value files. So here we have used this PD, that is a pandas.read CSV. This particular method has been called, and here the file name has been given with a proper path. So now this is my data frame, and if I want to print the data frame, the first 5 rows are getting printed because here we have gone for irish.head. So first 5 rows have got printed. So here we are having the 4 feature variables, that is a zipper length, sepal width, petal length, petal width, and the species will be the outcome variable. So this particular Irish dataset, we always love to use this one because it is very useful. Why it is very useful? Because all these values are within the inliers, there is no outliers, there is no null values, and in that case there is no noise in this particular or spike factors in this particular data set, so it requires very minimum amount of data processing, data pre-processing. So here we are having this Irish, that is the data frame. We have shown you the respective content. Now what we shall do, we shall go for the standardization. So here we are having this standardization, so that is our separating input variables and all the features. So at first we are extracting, you know that in the first 4 columns are containing the feature variables, so 0, 1, 2, 3. So that's why we have written this one as Irish dot columns colon 4. So that is the X. So let me show you that what is the current value in X. So X has extracted the first 4 columns of the data frame Irish. So that is my capital X. So now here we are extracting the respective Y here. So that is separating the target variables. I can have the different syntaxes I have tried. So this is the one which I'm executing. You can find that here we have extracted the respective what should I say, the respective outcome variable, that is the species we are having, and the shape is 151. That means here we are having 150 number of rows here. So here also if you go for the respective shape, you can find that you should go for here. So if you print this one, so there is 150 comma 4. So 150 number of rows are there. So why 150 number of rows are there? Because here we will be having 150 number of rows, where 50 rows for Setosa, 50 rows for versicolor, and 50 rows for virginica. So that's why we're having 50 plus 50 plus 50. So we're having 150 number of rows, and here the total size is 150 by 5 here. So 5 columns are there. So here I've taken the 5 by 4, and here we're having this there is 150 by 4, and here we're having this 150 by 1. So 150 by 5, that is the mother data frame. This is my 150 by 4. I've taken only the feature variables, and this is the outcome variable 150 by 5, 150 by 1. So now here we're going for we're doing the standardization of our features. Why? Because so that the dimension of these values will be very less. You know that whenever you do this standard scalar dot fit transform on this X, what will happen, the average of these values, the respective column values, will become 0, and the variance will be 1. So in this way we are doing this standardization so that we can have the very small values, and that will reduce the time complexity, computational time complexity as well. So here we are having this respective 150 by 4 standardized data in the form of array. Now see, here we are going for number of components. I want to get here 2. I can also make it 3, so that is not an issue. Out of 4 I am going to take 2 of them. So here we are going for one PCA, that is a class, this is a PCA object. So here we are passing n components is equal to 2. So now we are going for this fixed transform. We are passing not X, but the standardized version of the X, whatever you calculated using standardized dot fit underscore transform. So here you can see, again I'm showing the code. Again I'm showing the code here. So standard scalar dot fit underscore transform. Okay, now see. So here we are defining this particular principal components. There is a PCA. So PCA is the respective object, and then PCA dot fit transform this one. So now I want to put this one in the data frame with the heading, column heading, that is a principal component 1 and principal component 2, and here I am printing the respective shape also. You can find that 150 by 2 will be the respective shape, and here we are having the values, and values have become so tiny values, so that will reduce the time complexity. So I can also make it 3 here, and here I can go for so if I go for this, you can find that it is 150 by 3, and here we are having principal component 1, 2, and 3. So here we are out of the 4 feature variables, I have taken 2 of them after doing the scaling and after doing this respective component analysis, principal component analysis, I have reduced to 3 of them. So I'm going back to 2 again, executing the same. So it is 150 by 2. Next one, so I'm doing this concatenation. I want to concatenate that species column, that is the outcome column, and in this case I'll be going to have the output like this. So principal component 1 and 2, so they still there, and species has got added with this, and here the size has become 150 by 2 was the previous one, so it is 150 by 3. 150 by 2 was the previous one, here 150 by 3. So 2 principal components and 1 outcome column. So these are the respective values are there. So 149 starting from 0. So 150 number of records are there starting from 0. Okay, so now we're going for the data visualization, for the understanding that my data is still there as it is, but we are considering only the principal components. Sometimes what happens, you know, that whenever we are having 2 feature variables, very easy to plot the graphs. Whenever having 3 feature variables, we can go for 3D plotting. But whatever we are having, say 10 feature variables, 20 feature variables, in that case the graphical representation, the data visualization in the graphical form or map or graph or chart, whatever it is very, very difficult. So when you find our data in the data visualization form, it is very easy for us to comprehend. Otherwise it would become abstract to us. So that's why PCA is doing the job for us. It will select the respective principal attributes for us so that we can also go for the data visualization. So here we have defined the respective plot object and then plot dot set x level. So what will be the level of the x? So that is there. And then what will be the level of the y-axis? Title I have set. So here we are having the target levels, that is the Setosa, Versicolor and Virginica. Plot colors are this, and then we are having this 2 for loop variables. So there is a target comma color in Jeep, this one. I think this is not very getting clear to you. So what is this one? So I shall be discussing that one. So let me show you the graph at first so that the variables have got defined. So here I am going for the explanation. I shall come up to the previous cell, just give me some time. So here we are having the target labels. What are they? This is a list. We are having the plot colors. What are they? This is a list, RGB, red, green, blue. And here when you go for Jeep, target labels, plot colors, what is happening? It will take one component from here and one component from here, one element from here, one element from here. In this way it is form a tuple. In this way it will form a tuple, you know. For each and every iteration it will form a tuple. So now if I print this, if I go for say here say I comma j, if I go for this I comma j, and if you print this I comma j, you can find that what will happen. It will go for like this. So I will be taken the first component and j will be going for the second component. In this way we are going to get this one. I think you are getting my point. So there is a Setosa and then R, Setosa and R, Versicolor and G, green, and Virginica and blue. So in this way they are coming. So let me explain this particular graphical representation. What is the name of this graph? That is known as the scatter plot. What are you plotting on the x-axis? That is our principal component, and along the y-axis, that is our there is the principal component 1, this one x-axis, and principal component 2 along the y-axis. So see, everything I've done here. So I've defined this plot, that is my plot object, and then plot dot set x level. So there is a x-axis level. The font size I've given 15. I can also change it. This is my y level. This is my title. So this title has come down here. You can easily find this title has come down here. I've made the font size a little bit bigger for this. Then target levels are Setosa, Versicolor, Virginica, and plot colors are RGB. And then for target comma color in Jeep, target levels and plot color. So it will go for Setosa R, Versicolor G, and Virginica B in each and every iteration. So Irish underscore final df, whatever you printed earlier. So it was the name as Irish underscore final df. Df stands for data frame. So there I'm taking this Irish, that is a species column. So it is having the Irish, then Versicolor and Virginica are the values under this column. Whenever it is equal to target, then you are making this indices to keep. What does it mean, indices to keep? So here I can go for the print for the better understanding. So what I'm doing is that, see, indices to keep 0 comma true. So for the first 50 places it will be true, and then we'll be having false for the rest 100 rows. And then in this case we're having for the first 50 we'll be having our false, next 50 will be having our true, and last 50 will be having our false. We're not getting any true here because you know that whenever you print, and this whenever you're printing this one, actually it is printing the first 30 rows and the last 30 rows in this respective case. So here we will be having first 100 false and last 50 true. Why? Because it is the case of Virginica. So in this way, this is nothing but one Boolean array. So here we are going for, if this indices to keep is true, then the respective principal component 1 will be the respective column. From here we will be taking the value from this irish underscore final underscore df dot lock, and otherwise that will be plotted along the x-axis. Whenever the indices to keep is true, whenever it is false, the values will be omitted, will not be plotted. This is my case. And then c is equal to color and s is equal to 50, that is the scaling factor. So this color is actually this one. This color is actually this one, and s is the scaling factor. So in this way the graph is getting plotted, and then legends are getting printed. What is the meaning of this legend? Legend means what is happening, I'm just showing you. Legend means this one. This is my legend. Setosa versicolor Virginica. It is also showing the RGB, red, green, blue colors, and the respective scatter plots are also showing. You see the clusterings are still there, so no data has got tampered. But out of the 4 feature variables, I have taken only 2 of them, principal component 1 and principal component 2, and then plot.grid. So in this way you have seen that this particular PCA is also required for the data visualization, also to analyze the principal components, so that the rest of the components we can discard and we can work on with this principal components only. So I think you are getting my point, that how to apply this PCA and what are the advantages and what are the utilities we can get, and how to save our model from getting overfitted. Thanks for watching this video.